this video I'm going to talk about how to take the output file of the tree tracking R code that ends version H currently, but the same principles will apply if you've made other edits, and turn it into something you can use for machine learning, where each row is a case and the different features will be various attributes of the tree, the dependent variable being a binary code that reflects whether the tree died or not. So the first thing is you load the CSV in Excel, and again, you could do these things I'm going to show you in R or Python if you want to have it all locked up in one big similar format, or you could learn how to do it in Excel, which is kind of a nice skill to have anyway. So what I did is I added some new columns to that file. I just sort of randomly put them in the middle here so that I could have the new columns next to where it has tree status code, so I can actually look at it and understand better what's going on. First of all, first thing I did that's convenient, and I recommend this, is if you click in the top row, you go to View, Freeze Panes, and you freeze the top row. So I've done that. You can see I could scroll up and down and not lose the headings. The other thing I've done, which is kind of nice to do, is if you click over here in the left corner of the grid and you double click the one of the column headings, it fits all of the spacing of all of the columns, so you don't have to constantly be dragging and trying to figure out what the column headings are, because I've got some very long column headings in there. So anyway, I added a new column, and the first new column, now several of these columns, I did it in pieces so it was a little easier to see, but several of the new columns depend upon each other. But I'll just start with the first new column, which is a died or dead index. Now, if you recall, tree status code is the code that indicates whether or not a tree is alive or dead for a given time period. And if you recall, we'll just sort of go over, let's just look at this first tree in the file here. We have up to 6 remeasurements. We have in remeasurement time 6 for this one, we have that it's a live tree. 1 is live, 2 is dead, 3 is removed. So we're going to have to talk about those trees in a minute. As we can look at that tree and we see, oh, okay, what do we know about this tree? We know that the tree CNs from the different remeasurements, and here's the tree CN. Here's a little thing that you need to know. If you're working with CNs or trying to sort by CN, that kind of thing, you need to highlight the whole column by clicking up here. Then you go to the home and you go choose the number format, make it a number, and get rid of the decimal places. For some reasons, the filters don't seem to work all the time unless you do what I just did. It's annoying, but you have to do that for the CNs because it's such a long, crazy number. Anyway, we got the measurement year. This particular tree we're talking about was only measured in 1999. And I think I talked about this. The data, I wasn't quite sure. It might vary by state, but in Delaware anyway, the 1999 CNs don't match up with the ones beyond that. So you'll probably be ignoring 1999 data in these files. Or you could add the R code to make it 2000 as the minimum year. So we've got the measurement year of that. What else have we got? We've got the previous tree CNs, and that was all used by the R code to do the joining. What cycle the tree is from in this example, cycle 4. The diameter of the tree, 10.9 inches. We've got reconcile code, which is the code that tells you if the tree was removed or disappears from the inventory, why. You can check the library Excel file I sent you that has all the names of the fields and a quick explanation. And then we've got the status code. Status code, we've got a bunch of other stuff to the right, but we'll just stick with this for now. Status code of 1, meaning it was alive. So, what have we got here? This Excel works, it's kind of like in R, like nested functions, or in Python. So what I do, it helps you sort of study these things, is you normally in Excel, you see the formula bar that looks like this, right? If you carefully position your mouse at the bottom of the formula bar. You can drag it down to give yourself some more real estate to look at it, because some of the formulas are going to be multi-line. A convenient way to look at these things is to think of, if you position your blinker in in the formula bar, and you sort of use the arrow keys to move around, you can see that, and I wish Excel would do this better, but you can see that this parenthesis, as I go over it, the parenthesis at the end sort of goes, sort of shifts or does a little shimmer. It would be nice if it did it with colors, but it doesn't. Well, it does, but it's often hard to see. So that is the external function. So if I hold down the Alt key and I hit Enter, not a lot of people know this, and it's very convenient. Alt Enter, I can sort of rearrange the formula that I normally type all in one line, just for convenience, into multiple lines, so you can see what's going on. So what is this? So this match function is the key. So what the match function does, and when you highlight a portion of an Excel formula, it will actually show you in a somewhat convenient way, although it's still hard with the colors sometimes, what's going on. So what this match function is doing is saying, look for the value 2, in this example, in the array AX2 to BC2, which it highlights here for you conveniently. So it's this array. And look for an exact match. That's what the zero is a flag. It's like a search type flag. So it's not the number 0, it's actually just a flag that tells the function, it's a parameter. Look for the exact number 2. If it finds the number 2 in that array, it will return the position in the array of the first occurrence of that number 2. And I'll give you an example in a little bit. I'll scroll down. If it does not, oddly enough, the function just returns NA, an error, right? So that's why I wrap this function, this match function, inside the error function. You're going to see this in some of the other equations too, but I'm just doing this in depth so you can slowly begin to understand how Excel uses these wrapped functions. And if that error does occur, in other words, if the result of this match function is an NA, it says, well, instead of an NA, return a 0, because that's what the if error function does. So it's saying if error, happens because of executing this function, return a 0. And if, lo and behold, it returned a 0. Well, why did it return a 0 for the died or dead index? Well, because in this row, in this array, there's no 2. So let's go to the next tree and do the same thing. So here we are. It's 6. Well, what's it doing? It's doing the same thing, except it's shifted the array down to look in the next row. And we're saying, I'll do this again for you. Alt, Enter, and we'll do Alt, Enter. It's saying, look for the 2 in that array, if it and use an exact match for it. And if you find it, return the index, the column index 1, 2, 3, 4, 5, or 6, associated with finding that number 2. Otherwise, return a 0. Well, here you see it returned a 6. And why is that? Well, let's just count our column indices for this array. 1, 2, 3, 4, 5, 6. Lo and behold, it found a 2, which makes us happy. This next tree is odd in that it is a status code 3. Now, there's something about status code 3 I don't quite understand about our database. I think they started using status code 3, or maybe they only used it in 1999 or earlier inventories. So the point is, you can have a status code 0, I believe, and a status code 3. So In either case, we get a 0 here because there's no indication that the tree died. So what's my point? In this column, we have the column index that tells you when the tree first showed evidence of having died. Okay, well that's fine. What do we have here? Here we have, ooh, this one, look at this is an even more ugly equation, but again, if you want to, we could reorganize it to help it make it look a little bit easier to look at. We'll do Alt Enter, and I believe this ends that function. So again, we have this match function, but here we're looking for a 0. And the thing I just said about the status codes 3 or 0, that's what that's what this deals with. So we're saying, can we find a 0 in this array? If so, return the column index it's in. Otherwise, return a 0, because that's what this if error business is doing. So then, this if error is wrapped inside a another function or a procedure, which is a conditional statement. So here we're saying if this returns a 0, if this portion of the function returns a 0, then implement this portion of the function. Alt Enter. Right? Otherwise, return a 0. So the if then conditional statement has that format. If this, then that, otherwise that. So in this case, if this is true, if the function I described with the match returns a 0, in other words, it's not a 0 and a 0 doesn't occur in the array, then do this equation, right? And if that but if that isn't true, return a 0 again. So basically it's checking, in this case, I'm not saying this well, but it's checking for a 0, and then it's checking for a 3 in that array. And if both of them don't occur, then it returns a 0. That's what this does. So in this example, what we have done is, in this column where we're looking at these equations, we've found, again, as we did with the dead tree, this tree was removed. So we've got a column index of 6. And you'll see that the same thing occurs elsewhere if there happens to be a 0 that occurs in the array in this column. Okay, so for the next thing, we have the all alive, or the last alive index. So as we have the column index where it might or might not have died, which time period it occurred, column 6, we have a number here for the column index where it was last seen alive, which is kind of funny. Last seen alive. In this example, this in the same way I just described with the left inventory index column, the last alive index column wraps has a series of conditional statements wrapped within this if error routine that I described before. I could explain this. It's going to take a long time, but I think that if you study what I did with these two, you'll get the logic of how this one. There is one new thing in here, and that's the AND function that I use. And there's other ways to do this, and you guys maybe could think of a smarter way, but this is the way I do it. This function here, this evaluates to a true or a false. In other words, if I ran this independently, it would be a true or a false. And what is this doing? It's saying if if both BE2 equals 6 and BB2 equals NA, then, and if that's true, then do this, return a 0. Otherwise, return this other thing. And this 999 is just something I put in there as a warning. Like if you see 999, there's probably a screw up in this column. So there's probably a smarter way to do that again, where you don't have to type in this extra 999. I put it in there as a filler and as a warning to me that if I see 999, it's something to worry about. So, what does this mean? What this whole thing returns is the column index, as I did with the other two columns, of what column does the last known sighting of the live tree exist in. And in this case, it's column 6, because 1, 2, 3, 4, 5, 6. Here we are. We're in this column. That's where the 1 occurs for the first time, given it's not the conditional logic I just described. Okay, now with these three things, we can label each tree as to something that's more useful and is what we're going to use to filter the data set so we can do our model. So I told you about that AND function. So this is a little bit easier to see and talk about in pseudocode. So let's just do that. So if both BD2, if it did not die, and if it was not removed, or no, if it did not die, but it was, let's see here. Oh, no. If it did die, right, sorry. If it did die, in other words, if this was not a 0, in other words, it could have been a 1 through 6, and if it was last spotted alive at some point, in other words, BF2 is greater than 0, then label that tree as it died. What that means is there is a number in this column, and there's another number in this column. And we know that because this is going through time, oopsies, escaped. Because it's going through time, we know that the number, the column index of when it died is always going to be larger than the column index when it was last seen alive, because we go time 1 through time 6. So if we have a column 6 where it died, it had to have been alive either in column 5, 4, 3, 2, or 1. That's just something to remember about this. And I take advantage of that later on in the code. So anyway, we labeled as died. If otherwise, we have another if statement here. If BD2 is greater than 0 and BF2 equals 0, then it was always dead. What does that mean? Well, BD2 is the died index, so it died. But BF2, the last alive, it was never alive. Oh, well, that was always dead. Otherwise, if BD2 equals 0, in other words, it was not alive, it was not dead, rather, it was not removed, but BE2, or no, it was not alive, it was not dead, it was not alive, but it was removed. BE2 is greater than 0. And there are some trees like that, which are annoying. Well, for instance, this third tree, you see that it's NA for status code T1 through 5, but it's a status code 3. I'm like, well, the tree was removed. I don't know what that means, but I'm like, well, let's just say it was never measured. Let's just say they got to a plot, and again, I'm not sure of this, but they got to a plot and they found a stump, but they actually have no idea what was there. So anyway, that's how we deal with that case. And if BD2 equals 0, in other words, it did not, there's no occurrence of a 2 in this array, in other words, it didn't die, bf2 equals 6, meaning that the very last entry here is a 1, then it is alive. It's been alive the whole time. And if it's none of those things, then the tree was just removed. That's kind of like the one that, well, I've dealt with all the cases that I can think of, and otherwise it'll be removed. So I think I did this right, and again, this was 2 o'clock in the morning today, when I was doing this, but you can go through these, and you can check to make sure I didn't screw anything up. Like, for instance, this one's alive. Okay, it's got a 1 there, and it was only measured in that one time period. Let's just jump down, way down into here. We've got a bunch of 1s. Okay, here we've got some interesting stuff. This one, clearly it died in T5, it was alive in T4. Well, our died index has a 5, which is what we want, and it was last alive in time 4. It was not removed, because, you know, because what I just said, so we label it as died. And what else do we have? 222. This was always dead. 222. Do we have a 11111 somewhere? Let's see, I'm sure we do. Here. 11111. The last time it was observed alive was in time 6. Yes, we're good with that. Time 6. Okay. So that's good. So now, with all of this stuff, we've got everything we need. This is all building up to the grand finale here of, well, how do we mine the rest of the information in a given tree's row to get the stuff we need to do the modeling with? Well, let's go back to the first tree here, the alive tree, which was only measured once. It did not die. So there's no agent code when it died. Let's find a tree that died, actually, and this will be helpful for you, I think. Let's find one where there is an agent code. Died. Okay, there we go. So this tree here, and again, you can do this with any tree that's died, but not always dead trees, because apparently they don't have an agent code, because they don't know. They don't know. All they know is they went to the plot the first time and they found it was dead. This agent when died field, again, the conditional logic, and I'm using something fancy here, which is an index function. So this index function, I'm going to just sort of neaten this up a little for you. Alt, enter. There we go. So you can look at it just by itself here. We've got the classic condition. First of all, it's wrapped in a classical conditional statement thing. If this, then this. Otherwise, this. So you can see that. Inside there is this index function. What the index function does is it says, if I click in here, I've got this. For the array bn to bs 1277. So let's go over to bn to bs just to look at it. bn to bs. It's the agent codes. Okay, are you seeing what you can do here? This is the interesting thing. For that array, the row index and the column index. Well, the row index is I'm going to be looking in the same row. The column index is BD 1277. Well, what the heck's that? Oh, it's the index when it died in the T1 to T6 sequence, right? Find the value of, okay, well, let me just say this again. Search in this index, or in this array, for this row index, which is always going to be a 1, because we're always staying in the same row, and this value, which is BD 1277, which is um, the um, the column index 6. So find the value of this array that is in row 1, column 6 of the array. That's right. I'm sorry. It took me a little while to get to that. Again, search in this array, which we already saw was the row of agent codes T1 through T6. For T1 through T6, the values in row 1, column 6, and return it. And that is why in the 6th position, the 6th column of Bn to be BS, we've got the number 70, and that's why it returns a 70. Do you get it? I don't know if I mean, you're going to have to stare at this, but that's what this is doing. It's I've already calculated the column indexes for when the tree died, and I want to extract from somewhere else in the spreadsheet the corresponding row and column index. It's always going to be row 1, but column whatever, to get the one number that I want out of the array. Because otherwise, well, how do I know which value to look for, to use, right? I mean, I could be using any of these values. Well, I want to get the 6th value because I know that it's the 6th column where the tree died. And this 70 corresponds with when the tree died. This is kind of a clever trick that you can use in a lot. I use this kind of thing all the time in Excel. So anyway, I'm going to pause for a moment. Okay, I just said hello to Tanya. She says hello. Anyway, so for each tree then that has died, we have the agent code. If it's a 0 if it did not die, and it's what killed it. The first time it died in the record, and you'll see that this occurs. If it doesn't have to be T6, it could have occurred in any of the time periods. Okay, we're almost done, and then you'll be able to go crazy on this. Let's look at this next column. This is another, you guessed it, conditional statement. And what I've done here is I've used the same index logic. So, what does that mean? I'm saying if BF2 equals 0, it will return a 0. And what's BF2? Which that's the last time it was alive. Well, here it's not a 0, it's a 6 because the tree's alive. Otherwise, do this part of it, right? So this is the full, I'll just do Alt-Enter, so you can just stare at it by itself. Alt-Enter. Okay, so if it's not alive, return a 0. Otherwise, do this. What is this doing? This is doing that index trick that I told you about. It's looking in KB2 to KG2. And it's looking for column index 6. Right? BF2. Right. And it is dividing that by what's in MP, the corresponding value in MP2 to MU2. Okay, so first of all, it's KB to KG divided by MP to MU. Let's just remember that. Let's go over to KB2, see what we're working with here. KB2 is trees and saplings per acre. Okay, so let's think about that. Trees, so it's the number of trees and saplings per acre on the plot, and that's divided by something. K, what did I say? MP to MU. So it's 159.24 divided by MP to MU. So we have to go all the way over to MP to MU and see what we were doing there, which is the forest proportion on the plot. Now, it was a long time ago, but if you guys recall, we only measure trees mostly, but for your purposes, we only measure trees on forested pieces of plots. A plot can have more than one condition. It can have a non-forest condition. You guys drew out your plots, so you know what that looks like. So if you've got a plot and it's half of the parking lot and half forest, the forest proportion would be 0.5, 0.5. Here, since the total forest proportion is 1, we know that that plot, that tree was on a plot that's 100% forest. So you're like, oh, well that's good, I guess. So why am I doing this? Well, the point is, in FIA, when we calculate, the way I calculate it in the code and the way we do all the time in FIA, we do trees per acre of land. So a 6-acre plot is means that one tree measured on a 6-acre plot represents 6 trees per acre of land. Because of the, and that makes sense because of the way we do estimation. The way we are doing this for our study, however, it's not so much we're interested in using per acre of land. We're interested in, because we think that tree density per acre of forest is the thing that's going to be affecting mortality, not per acre of land. So we have to convert it to trees per acre of forest. What we do in order to do that is we divide trees per acre of land, which is going to be this, by trees per acre of forest, which is that. And in this example, you can see, because proportion forest is a 1, we divide by 1 and we get 159 point whatever, and let's just verify that, 159.24. If we go back over there to MP to MU, MU, where are we? And that's why this is one of the problems of working with this giant data set. It's tiresome, and I'm sorry about that. And you can actually filter this out and get rid of columns. Let's just scroll down here until we find one. Okay, so it's 0.22. So for this tree, it's measured on a plot. It's measured on the forest portion of a plot that's really only 22% forest. So the trees per acre of land has to be divided by 0.22 in order to get the trees per acre of forest, if that makes any sense. I can explain. If you guys are like, what the heck is he talking about? Just send me a text and I'll do a little worked example. It's easy if you draw it. Like draw a picture of, like say, oh, let's pretend the plot was an acre. Let's pretend it was only half forest and we measured 3 trees. How many trees per acre of land is that? 3 trees per acre. How many trees per acre of forest? And you'll quickly see, oh, I see, it's 6 trees per acre of forest. So there's 3 trees measured on a half acre. That's how you can convince yourself, oh, I see what he's doing here. He's dividing by the proportion to get the per acre of forest. Okay, let's go back to our yellow columns here. Here we are. So you might have missed this. I have BF65 here, as opposed to the, like, what was the trees per acre when it died, or the or the proportion of forest when it died. just take note, and again, this is where you guys need to be thinking. I have for each time period the trees per acre, right? So I'm like, okay, if I have the trees per acre for each time period, but the tree died, well, what I probably want to do, the thing that caused it to die might be the current trees per acre, or it could be the trees per acre at the time when it was last alive. The trees per acre from when it was last alive are probably what affected the tree between, for example, time 5 and time 6 that caused it to die, potentially. Maybe, and again, I don't know this, but you know, generally, like if there's more trees per acre on a plot, more trees tend to die because they're all fighting for limited resources. So instead of accessing the column index when it died, I'm accessing the last alive index, if that makes sense. So you can see I've left some empty columns here, and you can add new empty columns. I just left 3. Here's another column, and again, it's the same logic. So for example, what was the damage type when the tree died, using the same index, right? The tree was dead. Well, what on the plot when I showed up and it was dead? Well, gee, there had been some damage on that plot, or on that condition where the plot was. What was it? And that's what's going to be in this column from this equation. So what do you guys need to do, given everything I've just said? And you know, you could do this in Python or R, or you could do it in Excel, because we're kind of, we can move out of there if you want to, and if you want to learn about Excel, because you can see this is kind of cool. You need to add the appropriate columns that you want to model with, and I'll just sort of work through this with you. We already got agent code. We already got the damage type when it died. We already calculated trees per acre of forest when it was last alive. So these things can be predictors that predict whether or not the tree is alive or dead. Well, what else? Well, we've got a whole bunch of other stuff in here that's in the same format that we could choose from. For example, for that tree, oh, well, maybe it's not really trees per acre, it's carbon when it was last alive. That's going to be of interest because, you know, while they might be somewhat correlated, trees per acre and carbon is kind of like the amount of trees there, right? You could have a lot of little tiny trees and small carbon. So this might actually be a better predictor than trees per acre. So you have to do the same thing we did with trees per acre for carbon. What else? The height of the tree? Could that be? Oh, well, I need to get the T6 height of the tree because that was when it was last alive, using the same logic. Volume? I don't know. Well, carbon and volume are pretty highly correlated, but maybe not for the giant trees. Maybe that levels off, so it's not a one-to-one. So instead of that, I'll use volume. Species code. Oh, okay. Well, obviously, for some species, the same density and other stuff might make the tree die, whereas other species might be resistant to dying. So maybe species code, or maybe I want to filter and run my model separately for each species. Lat long. Road distance code. This is going to be annoying because, again, here, if you remember, we're in 1999. I don't think they measured road distance in 1999, so it's an NA, so it's a missing value. But for the other years, you might be able to do distance to a road. Okay. Treatment code. Oh, well, there are treatment codes. And again, look at that library I sent you to quickly and conveniently consult what treatment code means. And again, we've got the different treatment codes, the primary, secondary, and tertiary, which is annoying. Stand origin. Oh, was it planted or natural? Well, maybe planted stands behave differently than natural stands. Here's the disturbance code. These are the primary, secondary, and tertiary. If we scroll across here, the year of disturbance, that's probably useless. What else have we got? plot CNs, which we use. Damage agent, I think we already talked about that. The different codes, primary and secondary, I think. Damage location, that might not be useful. The damage type, the damage type, that might be interesting. Again, just consult the codes. We've got elevation of the plot. Okay, the forest type of the plot. Well, that might have some impact. Owner code, does it behave differently in public and private? Stocking class, I bet you anything that stocking class is going to be an important one. So it's stocking class 2 here. The slope percent, the aspect. And then we've got the carbon on the plot. We've got the standing dead carbon. How many other dead trees are there? All these things that could be predictors that you need to run through this procedure. Like use the same equations to calculate the appropriate value, the yellow value, which is the thing that you're going to use in your machine learning model. So all these yellow columns that you guys are going to construct based on your own common sense and everything we've talked about up to this point will be what you use to model a binary variable. Is it alive or is it dead? And you'll obviously want to use some of the stuff to the left here too, which is the diameter, tree diameter, which is to the left. So, one last point, and that is in this code has died, always dead, never measured or removed. I think the smartest thing to do is to say, well, I'm going to filter all my trees to a subset of these. For instance, never measured is obviously not going to be relevant, so I want to remove from my analysis all the never measured trees. Obviously, I want to have alive. Does it make sense to use always dead? No, because it never, it was always dead. I don't know why it died. It's not relevant. What I'm interested in is saying, well, there's a tree here and the same tree on a different site. And oh, they're both being measured through time. One of them dies and one of them doesn't. Well, why did the one die? What's different about it? Well, was it species? Was it the site characteristics? Was it the density of trees on that plot? Was it its diameter? Was it some combination of these things? That's the question your machine learning model is going to ask. With this stuff, just forget about mortality rate. I mean, we could, and I spent a lot of time trying to figure that out, but I would just ignore it. I would be like, yeah, forget about mortality rate. We're gonna use a different data set to look at mortality rates. So I'm gonna stop the video here, and I'll do a separate one for that mortality rate. Good luck. I know this is a lot, but you guys can do it. And I think especially this yellow strategy will get you on the right path to doing your machine learning models and do some really cool stuff. Shift, Alt,